All right, welcome back to another calculus lecture video. In today's lecture, I want to talk about kind of an interesting subject, which is the idea of computing derivatives using an implicit relationship between the variables x and y rather than an explicit relationship. So what do I mean by that? Maybe let's kind of talk about that. So up till now, we have only considered functions of the form y equals f of x. That is, y explicitly depends on the variable x. So that is, y depends explicitly. That is, you can just write down exactly what it is in terms of the variable x. However, this is not the only sort of case that we can deal with. We can look at other examples of functions in geometric objects where the relationship between the variables x and y is implicit rather than explicit. And perhaps the simplest example of this is the equation of a circle. So example. So the circle of radius, and we'll just do, I don't know, 2, is the set of points x comma y, so all the pairs of points x, y in the Cartesian plane, such that x squared plus y squared is equal to the square of the radius, which is 4. And if I were to draw a picture of this, then, well, it looks exactly what you think it's going to look like. So here I go, and I'm going to attempt to draw a circle. This should be pretty funny. So the circle of radius 2, which is already not a circle in that I've drawn, but the lemon of radius 2, more like, you know, it's just the circle centered at the origin, where all the points are a distance 2 away from the origin. Okay, so in this equation isn't described by just, or this object is not described by one sort of equation where y is a function of x. We sort of have the top and bottom halves of the circle here. So the top half, if we were to solve this equation, we'd have to take a square root to get y by itself. And when you take a square root, you have to take either the positive or the negative square root. And so if you take the positive square root, you get the top half, and y is going to be equal to the square root of 4 minus x squared. And the bottom half is likewise the same thing, but you just negate that. So this is the negative 4 minus x squared. And these individually just give you each of these pieces. So the bottom half right here and the top half right here. Okay? Again, really bad circle. I'm sorry. So implicit relationships sometimes can give you explicit relationships, but this is not always the case. Sometimes you can have quite a complicated expression and you can't actually solve for y in any way, or at least not in some intuitive or simple manner. Now, although we don't have an explicit relationship for y that's always true, well, I can certainly still just draw a tangent line on this object, right? I can place a point here and draw my tangent line, or I can place my point over here, draw my tangent line. So we can still compute tangent lines. We can still compute tangent lines. And to do this, we're actually going to differentiate the entire equation and use the chain rule in order to do this. So maybe as an example, or a continuation of this example, let's try and compute what the slope of this tangent line is at every single point. So if I give you a pair x and y, I want to know the slope of the tangent line at that point. So at a point xy on the graph or on the circle, what is the slope of the tangent line? Okay, well, if we want to do that, let's go ahead and just turn the page so we can have some room for our computations. So our equation is x squared plus y squared equals 4. Well, we can think of y as a function of x, at least locally around a point x. If I zoom in on the graph, you can think of any small piece of it, there is this sort of well-defined object, perhaps excluding a few points where you have a vertical tangent line or something like that. But our analysis will reflect that as well. So if we think of y as a function of x, then if I differentiate this equation with respect to the variable x, then what I'm going to get is this first term will just differentiate as normal, but then I'm going to have to apply the chain rule to differentiate this. So let's go ahead and see that. So dx of x squared plus y squared. This is, well, 2x for the first derivative. And then the derivative with respect to x of y squared, I'm going to write this as y of x quantity squared. And now what do I have? I have an outside function, which is just the squaring function. It's x squared, so I just take the inside and I square it. And then my inside function is y of x. And so this, when I differentiate it, is going to just give me, well, the derivative of the outside function, and then I plug in the inside function, and then I have to multiply by the derivative of this inside function, y of x. Well, I can just write that down as, and I'll write it in the form dy dx, just because it's standard notation in these sorts of problems to use this instead of the prime notation. And then notice I've differentiated the left side now, so I've got this thing. This is the object I'm interested in, the slope of my tangent line. And now I need to differentiate the right side of the equation. Well, that's fairly straightforward. It's just 0. So dx of 4 is just 0, because it's a constant. It's not changing with respect to x. Okay, so what have we shown? So 2x plus 2y dy dx is equal to 0. And solving for dy dx gives dy dx, well, subtract the 2x over and then divide by 2y. This is going to equal negative x over y. And so at any point on my circle, I can compute the slope of the line which is tangent to the circle at that point. And its slope is going to be this quantity. Notice that if y is equal to 0, so I'm at one of the 2 points on the circle, if I look at this 0 here, I'd be at either this or this point, then my slope here is going to be sort of, it's infinity. I'm dividing by 0. And that we can think of as corresponding to a vertical tangent line. So in this case, dividing by 0 sort of has a geometric interpretation in that it just represents your line being vertical. Okay, so this is how we can compute slopes of tangent lines when the relationship between x and y is implicit rather than explicit. So let's do another example of this just to really get our hands dirty. So example 2, or just another example. So let's do this. Let's find all points where the tangent line to y cubed minus xy equals 6. So this equation represents some set of points in the plane, and we can compute the tangent line to it at any point, at least on the graph. Find all the points where the tangent line to this is horizontal, so the slope is 0, or vertical, where the slope is infinity, or I'm dividing by 0 in some place. Okay, well, first of all, I need to compute the slope of the tangent line, and then I can figure out where it is horizontal or vertical. So let's take this equation and differentiate it once more with respect to x, using the same sort of idea as we did up here. So d dx of the left-hand side. So this is equal to, here I'm cubing something now instead of squaring it. So I do the same thing I did up here, and I'm going to end up with 3y squared, and then I multiply by the derivative of y, so dy dx. And then here in this second term, I have a product of two things, so I have to use the product rule. So I'm going to subtract, and I'm going to put this in parentheses because I don't want to miss my minus sign anywhere. So I do, for the product rule, we do the first function times the derivative of the second function plus the second function times the derivative of the first function. Well, the derivative of x is just 1, so we'll leave that as is. And then, of course, the derivative with respect to x of -6 is just 0. Okay? So we've got that, so let's just write this down. So 3y squared dy dx minus x dy dx, and then the minus sign distributes to the y, so minus y is equal to 0. And now what I want to do is solve for dy dx. And so what I can do is I can move this y over and then factor out a dy dx from each of these terms. So I can write this as dy dx times 3y squared minus x. So I just factored it out of each of these two terms. And then I'm going to add my y over. And then what's left to do is we just need to divide. So dy dx is equal to y divided by 3y squared minus x. Okay, so there's the slope of my tangent line. If xy is a point on my graph, then I can compute the derivative, which is the slope of the tangent line, using this equation here. So now we've got the slope of our tangent line. Let's go ahead and turn to this analysis where we try and figure out where this is 0 or infinity. Well, if dy dx equals 0, well, the only way for this to be 0 is for the numerator of this fraction to be 0. So then y equals 0. But if y equals 0, we also have to satisfy this equation right here. And if y is equal to 0, then 0 equals -6, which doesn't happen. That's absurd. So there are no points with horizontal tangent lines. Okay, so I checked what condition I had to have on the derivative in order to have a horizontal tangent line, but then I also have to check that the points which satisfy that also do in fact lie on my graph. But in this case, that doesn't happen, at least for horizontal tangent lines. None of these points exist on the graph. So let's turn the page and do this for vertical tangent line. So again, dy dx is equal to y divided by 3y squared minus x. So at a vertical tangent line, the denominator here has to be 0. So for the tangent line to be vertical, we need 3y squared minus x equal to 0. Well, notice what this means. This just means that, so that is, if I just move the x over to this side, I need x equal to 3y squared. I need x and y to have this relationship between them. Now, what we can do is we can take this relationship and plug it back into our original implicit relationship between x and y. So we also need y cubed minus xy equals -6. And so what we actually need is y cubed minus, I plug in my 3y squared for y here, or for x here, 3y squared times y, which is equal to, well, this is y cubed minus 3y cubed. So this is -2y cubed, and then this is going to equal -6. And now I just divide by -2. So I need y cubed equal to 3, or y equal to the cube root of 3. And just for fun, this is about like 1.442, something like that. Okay, so again, what did we do? We took our derivative, the slope of our tangent line, we checked the condition for the tangent line being vertical, and that was the denominator being equal to 0. And when that's the case, we have this relationship between x and y, that x is 3 times y squared, and then we took that and plugged it into the implicit relationship between x and y that we started with. And that from that, we were able to deduce a condition on y itself. And now if we plug this y back into here, we could also deduce a condition on x itself, or we could plug it back into here. Either one would give us the same answer. Okay, so there's all of that example, and these are the, we're done now. We don't have any more points to consider. And I think it's nice to maybe see the geometry of this. So through the magic of video editing that I should have been doing in my lectures a long time ago, I can transition to this. And this blue graph here, if I scroll up, I've got some code that's producing this graph. And this red line is the tangent line to the graph of that implicit relationship. So the y cubed minus xy equals -6. And as I vary my y value, you can see that I'm actually constructing the tangent line at all these points. And if I put y equal to about 1.44 roundabout, so the y-axis is this vertical axis, and if 1.44 is around about right in here. And so if I put my y there, you can see that I am having to pass through this point where I have a vertical tangent line. Okay, and so we were able to deduce this exact value for y doing this purely abstract sort of analytical analysis. That was a very redundant statement. But anyways, yeah, I think there's some nice geometry happening here, and this shows that you really do have graphs of functions even though you don't have an explicit relationship between x and y, but you do still have points satisfying this implicit relationship. And because the graph of those points is smooth, we can still essentially do calculus on the graph. And that's really what we've done here. Okay, so that's everything for this video, and I will see you all in the next one.